Hello everyone. My name is Hongru Wang, and I'm a final year PhD candidate from the Chinese University of Hong Kong. So today I'm so happy to share one of our accepted paper by ACL 2025, which is self-reasoning language models with lots of wonderful researcher and institutions such as Bit State and the University of Edinburgh. So in this work, we focus on a very hard problem, inference time scaling. So the DeepSeek R1 and OpenAI's O1 model has proved the successful of a success and the effectiveness of inference time scaling, which the model spent more time to think and reason about a given task or question during the inferences. However, most of previous method or models such as O1 and DeepSeek R1 use the outcome-based reward RL reinforcement learning to achieve such inference time scaling. However, this paradigm brings several limitations and disadvantages. So first of all, we do not always have this outcome-based reward. We do not have this always have these supervision signals for most of tasks in practice. For example, open-ended question answering. So in DeepSeek R1 and O1, they mainly focus on the math and the coding task. So in practice, there are many other tasks, right? So we do not have the outcome-based reward. And secondly, the reinforcement learning usually require much computation resources and lots of GPUs to achieve a very high performance on the downstream tasks. So in this work, we focus on one question that could we acquire this kind of the inference time scaling capabilities by directly fine-tuning the model instead of using the reinforcement learning. So to achieve this goal, the key lies in generating and obtaining high quality and longer COT data doing our to fine-tune our model, right? So with longer term thoughts during the inferences, this model can explore more creative and diverse reasoning rationales while sampling various meta-reasoning skills observed in the O1 and DeepSeek R1, such as decomposition and reflection. So the idea is simple. So in previously instruction training dataset, usually we give the input, the question and the task. We want the model to generate the intermediate rationales and followed by the final answer. So in our self-proposed self-reasoning language model, we want the model to give the input X and the previously rationales. We want the model to generate a much longer and corrected rationales and followed by the final answer. So in this process, we just use prompt, meta-reasoning prompt here to trigger the behavior of the model to generate much longer COT, this kind of the data. So specifically, we introduce self-reasoning language models, SRLM, as shown in this figure, where the model itself can synthesize longer COT data and intuitively improve the performance through self-training and self-evolving. So the self-reasoning language model can act as both types of model. Types of model. So the first is it can act as a response generation model, like learn to reason, and secondly, it can act as a reasoning model to refine its own reasoning rationale, such as how to reason. So it is noticed that we do not do continual training. We usually doing each iterations. We just train the model, fine-tune the model from the base model instead of the from the model in last step. So here, figure 2 shows the general framework of our proposed self-reasoning language models. So it can consist of two phases. The first one is the reasoning catalytic acquisition, and phase 2 is self-improved LLMs. So in phase 1, so we just use borrow the off-the-shelf instruction training datasets, and then we use meta-reasoning prompts. For example, we define several meta-reasoning skills, and we add some explanations. We want the model to use these different skills to expand the original short COT data into a longer COT data. So by this way, we can collect lots of the reasoning capacity data sets. We just use very few this kind of data. In our experience, we just use 1,000 samples. However, the size of our instruction training data set is 15,000 data samples. So in this recent cases list data set, we have the X, and we also have the arranged originals, and then we have a much longer version of the original. So basically, the input is X and R J0 here. Output is R J star here. So and then we just mix the original instruction data set and the get the reasoning capacity data set, mix this kind of the two data sets and fine tune the base model, and then we can get our self-reasoning model in first iteration, and then we can directly feed the full set of the instruction training data set into the M0 here to get the new instruction training data set, which has a much longer COT regionals in the compared with the original COT regionals, and then we can do some regional selection, and we can use this as a new instruction training data set in the next iteration, and then follow a step-by-step iteration by iteration to iteratively improve the performance of self-reasoning language model. So that's basically the idea, the key idea. So and here, let's dig into the specific detail of the phase one and phase two. The phase one is a reasoning catalytic acquisition. So in there is a Chinese poem that is it's better to teach a man to fish than to give him fish. So in this phase, we define lots of the reasoning modules as internal cognitive tools. For example, we can define COT, reflection, critique, summary, decomposition, reflection, etc. And then we can use a powerful teacher model to generate such capacitic data. We only get 1,000 such data samples in our data set. And in phase two, we just use iterative reasoning expansion and then iterative reasoning selection. So basically, we define three different selection strategies. The first one is a length selector, and second one is off the policy selector, and third one is the on-policy selector. We just calculate the probability of the giving the X and the original to generate the final answer. So we just compare which probability is much higher compared with use the base model or use the self-reasoning language model in last iteration. So length selector is very easy. We just compare the length of different regionals in different iterations. Okay, here are some experience results. So first of all, we can find that incorporating additional regional reasoning expansion samples into the instruction training data set act as a catalyst leading to improved performance, which is advanced by the self-reasoning language model in M0 is much better than reflection training, and also the MagPi, which is a vanilla version of the use original MagPi instruction training dataset. And secondly, we can find that small SRLM can generate high-quality regionals iteratively. So it is evident that SRLM with different selectors at various iterations all leads to improvement compared with the initial SLM M0 as a very first time step. And all types of the selector outperforms the first time step SRLM with the unpolicy selector excelling in MMU, while the length selector performs better on higher SWAG and BBH. Okay, here we also did some lots of the analyze. For example, we did the best of n sampling. We just increase the sampling time from 1 to 64. We can find that compared to baseline reflection training, we can our proposed SRM can explore more depth, diverse, and creative reasoning paths as we can find the gap became bigger and bigger compared with the baseline. So which means our method can explore more depth and diverse creative reasoning paths to achieve the correct answer, especially when the sampling times increases. And secondly, we also did some observation study by removing the catastatic data in each iterations. We just use the purely instruction training data set to prove the quality of the generated instruction training set by our SRLM in different iterations. So we can find that the performance at the later iterations mostly outperforms the performance as the initial iterations. So which means our proposed self-reasoning indeed generate high quality instruction data set compared with the instruction training data set in the first time step. And here is means the iteration 0, which is the instruction set is generated by the GPT-4o. And secondly, we can find that when incorporating reasoning statistic data, the improvement can become more stable and consistent compared with the only instruction training data set. And thirdly, we also observe that supervised fine-tuning memorized the philosophy, these kind of observations. So first of all, we draw a skill distribution during the instruction in the instruction training set, and also we draw the same distribution doing the inferences on these different test benchmarks. We can find this kind of the training distribution and the test distribution are very similar. These can all these meta-reasoning skills during reasoning and inferences are very similar, and also, for example, the top three meta-reasoning skills are exactly same. So this means if we simply use the supervised fine-tuning method to fine-tune the model to acquire such inference test scaling capabilities, we must be very careful about which kind of the meta-reasoning skills or what kind of the data that we created. And more analysis can be found in the paper, such as different way to construct the reasoning catastatic data, and different way to update the catastatic data, and also the different source of the instruction training set, different types of the base model. So I encourage you, if you are interested in our work, I encourage you to read our paper. Yeah, basically that's all. And here is some conclusion. So in this work, we introduce self-reasoning language models. So while the model can synthesize longer COT and iteratively improve the performance through self-training, it can act as a response generation model, learn to reason, and also act as a reasoning model that to refine the originals, like how to reason. So in this work, we do not assume anything about the answer, such as a format and correctness. We just use the shape instruction training data set. And secondly, we present reasoning cassette data function as a demonstration to get the LM to unfold hidden reasoning chains with the augmentation of various meta-reasoning skills, such as reflection and composition. And thirdly, our proposed self-reasoning language model achieves a very significant improvement of more than plus 2.5 points across 5 different reasoning tasks on 2 backbone models. And also it brings much more improvements with more times of simply doing inferences, prove the great potential of our inference time scaling. So I think that's all. If you are interested in our work, please do check our paper, and also welcome to any discussion and comment. If you can email me or just WeChat me or Twitter me. Yeah, I think that's all. Thank you very much.